It died.
And what with it right now?
It's the 13th, although it's not Friday. It's a little slow, so I pulled it up with the ambient right now. Okay, so over the last 8 years, Daryl's career is focused on security research, security assessment, pen testing, consulting for corporations and government agencies. Conducted security research on numerous technical subjects, releasing white papers, security advisories, and presented the information at numerous national and international security conferences, including Black Hat, DEFCON, SchmootCon, DerbyCon, RSAC, and Hack in Paris, which I heard you just got back from about 2 weeks ago. So maybe you can get a little bit more insight on that one. That sounds like fun. I want to go to Paris. Next time you go, you need to call me. So, yeah. Oh. Just hand it up and whatever you do. Alright, so Deral has been interviewed and quoted by several media outlets and publications, including the BBC, MIT Technical Review,
NBC, SC Magazine, Threat Post, and The Register. So, anything you want to add to that there, Deral? Oh, and he doesn't really admit to this either, but I've asked, but he is prior Navy. So we have a little connection there, even though he was a submariner, right?
Yeah, were you on the target?
I was on a target, according to you, right? So, but you were targets to us, so we would hunt you down, right? So, anyways.
Thought you were doing that.
Yeah, we thought, yeah, you guys were hiding somewhere. Yeah, so, but, you know, that's in inter-service rivalry here between the Navy guys, between surface and subsurface. And then we got the service rivalries that are between the Navy and the Air Force being here at Wright Pat. So I like picking on the Air Force too, so I might throw a few jabs out there as well. Anyways, all right, so let's turn it over to Deral and let him. Yeah, this one's for the house. That one's for the.
Okay, here we have the house one. That's why I got pockets. So it's great to be here, which I always enjoy. 13 years is kind of amazing. I never thought this would happen when we started this 13 years ago. So that's pretty good. So in today's presentation, we're going to be going over some UBoot stuff. We're going to be covering a couple other simple things. But generally, we're going to be looking at some various attacks against devices that can be used. Now, if you've gone to the monthly OISF meetings, you may have seen fragments of some of the stuff I'm going to actually show and talk about today. Let's go ahead and get started. So we're not going to have a lot of slides here. This is very much demo intensive, to say the least. So what is UBoot? Universal bootloader. It's basically what it is. What does it do? It loads data from flash memory. It makes the system come up and run. It loads the kernel and it executes it. It passes various arguments or commands to the kernel during the boot process to get it to do certain things that you want to define. It's accessible via a serial console in a lot of cases, unless they've actually shut that off. And it has minimal commands, and we're going to actually look at some of those command structures of UBoot here in a little bit. So why attack UBoot, other than because you can, you know? I think the thing is to gain root access. Often, if there's any level of security been added to the device, the vendor would have actually put a root password on there, made it fairly complex, or set it up that you can never actually log on with root itself. I've seen cases like that, add these levels of complexity. So the goal often is, hey, if I have a piece of hardware and I want to get root level access, There's a number of reasons why I want to get root level access. One may be, hey, I want to be able to pull the firmware off. This is one method to do it. If I can log on, I can easily transfer the firmware out of the flash memory, either across the network to a USB or some other means to actually extract it off there, versus having to get onto the device with JTAG or serial wire debug or some other debugger or physical taking chips off the board. By getting this level of access, it makes it possible for us to do that. And we're actually going to be doing an example of that today also, of pulling some of the firmware off over to USB. And one of the issues I ran into in one of these devices, this particular device, when referencing the USB memory stick. So, one of the first things you want to do when you're actually looking at any device, if I don't break my neck here, is you want to actually dig into the actual hardware and really understand what you're looking at. So I got a number of things marked out here. And this happens to be a Luma, which is a mesh Wi-Fi device. So that's another typical current IoT technology, but in this case is for creating a mesh Wi-Fi in your home so that your entire house is covered with Wi-Fi evenly and you transition from device to device to device seamlessly as you move through your house with whatever technology you have. So in this case here, there's a number of things. I don't know if this thing has a laser pointer or not. It won't work on this. Should have brought my green one and everyone would be like, ah! I don't know if anyone's ever seen that. I had a green laser pointer, and I would, whenever I used it, I'd turn around and point at the screen. It didn't know that the first 3 rows of every time I did this, everyone would go, because it was so bright. And then one time I was passing through, was it Sweden with it? Turns out laser pointers are illegal in that country. So I was just traveling through the airport, so they actually pulled me and put me in a holding room and had to call the cops in because I had this laser pointer that was like 50 milliwatts. And I think the highest level you can have there is like 5 milliwatts. So it was 10 times above legal limit. So it's great, but it's a little bright. You can use it instead of a flashlight and go into a dark room and just shine it and the whole room will light up. But that's another story. So this is a typical breakdown. We have a number of pieces here, and I think you can see most of these. Underneath this shield here is the RAM. I should have taken this picture without the shield. So one of the cool things when identifying RAM when you're looking at a device is you find a chip on there and you see the lines the circuit board runs going to it, and these ones will zigzag. When you see the zigzag lines showing up to a chip, often that means RAM. RAM's usually interfaced in a parallel fashion, and these function as delay lines, so all the circuit lines on the board are the even length, so they'll squiggle them around. It's a good indicator. And then ARM processor. And then underneath these shields are typical various RF type devices. And there's also a number of headers on these devices. Here's one right here. This is the header we're actually going to use. These don't typically come on the board, so you have to solder them on to be able to access and connect into it. And this right here happens to be a flash chip. In this particular board, there's actually 2 flash chips. There's one on the back side of it right below this one that is a smaller SOIC8 footprint, and it actually contains UBoot. This one contains the kernel. Which makes the attack that we're going to show in a little bit to get into UBoot a little more easier because there's a lot more delay within there because they're 2 chips. So one of the first things we want to do is, as I mentioned, for UBoot, you want to get access to a serial console. So how do you identify a serial console? There's a number of tools for doing it. The JTagulator is one example. It has the ability to hook up to all the pins on a device, and you run the JTagulator for the UART function, Universal Async Receive Transmit, and it'll go through all the different permutations of the pins, feeding data in and out, and it'll identify which ones receive, which ones transmit, and it'll also identify the baud rate, or the bits per second functionality of the actual transmit and receive. You can also use a multimeter. In multimeters, you're actually going to measure voltage variations. I think that method totally sucks, and I'm thinking, why in the hell would you do that? There's way much easier ways of doing it. One of the ways I like to use is a logic analyzer. So I use a Sele logic analyzer, and I've probably showed this in monthly meetings quite a bit. It's a great little device. You can buy them really dirt cheap. You can pick them up for 10, 15 bucks. I've never used a $10, $15 one, but apparently they work for most technology because most stuff doesn't have that fast of a bus. This one here is about a $700 one, so it's a little pricier. This one's high speed and it has 8 channels. So one of the things we want to do is go ahead and test for that. So we're actually going to do a demo. So we're going to move over. I'm going to do a quick logic analyzer demo here. Come on. About these VGAs, they change my screen size so bad. Yeah, well, it's the way it goes sometimes. So what we're going to do is we're going to actually hook everything up here. On these logic analyzers, you have these cables here. The top, so we have 2 channels on here. In this particular case, the top wires are the actual channels, and there's 4 of them. They run from black to orange. The bottom ones are actually ground, and they're all the same, so they're all equal. In this particular case, I do know which is ground on these pins because I like cheated and read ahead in my presentation. Power source is USB for this. And then I'm just going to hook a couple up here so we can get a general idea of using this. But if you had, let's say you had 8 pins, or 8 pins you wanted to check, you could hook all of them up with the logic analyzer. And then I would use a multimeter and trace out looking for ground. Often ground would be tied to the main back plane of the board or some kind of shielding. The shieldings would be ground. So you can take one of the shieldings and measure from it to one of the pins and identify ground that way. There's one method for doing that. So let's come over here too. So here's the Sele logic analyzer. Let me go ahead and clean this up a little bit. It's going to be a little hard to see because this thing changed the screen, but I don't know how it looks behind you. So right now we actually have 3 channels on this. We can only hook 2 of them up. But we can go ahead and run start on this, and what it's going to do, it's going to take samples, and you set the sampling rate and how long you want it to run. Here we got it run. We'll set it for 20 seconds, 20 milliseconds. Sampling rate runs for 20 seconds. We're going to look at these first 3 channels to start with, and then what we want to do is we're going to go ahead and hit start, and then we're going to plug this thing in. So we want to capture the device during power up. So if we hit start, and then hit power up. Let that run for 20 seconds. Make sure it's running. Yeah, there's blue lights on the bottom, so we know it's spinning around. So at this point, the device would go through and would go through the UBoot process, boot things up. So here we are. And if we shrink this down, we can see we actually have data on one of these channels, on channel 1. Okay, fairly straightforward, but we want to decode it. Logic analyzers have a number of different decoders. Let's show more all the analyzers so you can see, hopefully you can see that. That's not bad. So you have all these different analyzers, SPI, CAN bus, JTAG, Manchester encoding. So there's all kinds of stuff here, but we're interested in ASIC. That's what we're looking for. And I can quickly think of this as being async, mainly because, one, we don't see all these channels with data flowing on. If you hit a bus or a header and all the channels have data on it, It's probably going to be some other type of communication protocol. Often when I see that, I can go look at that and find out, and I've seen this in some cases where it would be SPI, where you have data in, data out between two devices. That'll show multiple channels where you have a clock channel, you'll have a data channel, you'll have an on and off channel, and then you'll have another data channel. Typically that's not going to be UART. But in this case, where the channel, the pin before it and the pin after are blank for the most part. So we know it's more likely that this is probably asynchronous communication. But the best way to tell is you want to be able to use a asynchronous decoder on it. And that's what we're getting ready to do here. So we know it's channel 1 is the channel. Next thing is figuring out the baud rate. And that's kind of interesting. There's a whole series of standard baud rates. Most vendors will use one of the standard baud rates. They'll often use 8 bits, 1 stop bit, no parity. It's very common. It's typically what you see. I've only seen something different one other time. I was doing a test on a device here a number of months ago, and it would boot up and you could actually see the data flowing, and then all at once it would just scramble. As soon as the kernel loaded, it would scramble. Turned out they were actually changing the parity bit in the middle of the flow. So as soon as the kernel loaded up, they changed the parity bit on the communication and totally messed it all up. And it took me a while to figure that out, so it drove me crazy. But you need to pick one of the standard baud rates. And often, you usually see, I think it's what, 384, 56700, or 115200. 115200 seems to be the most common. Some really easy, I just guess it. If you decide it's not one of these, there's the automated function that was there. So you could actually do the automated. That's iffy. It works maybe 20% of the time. The rest of the time it doesn't work worth a shit. And then also you can actually measure it. So if you take one of the, right here, the narrowest pulse, and you take that measurement and divide that into 1 second, you're going to get the bit rate. So if you like doing math, I don't. I prefer just guessing. It's way much easier. So as you see here, I don't know if you can see that over to the right of the screen up here. You can see it says format log. What we're seeing here is the device boot up. We can also see it at the top. See across the top there? Serial. And if you go down through here, you eventually see boot. So we can see, so now we know that we're looking at asynchronous communication. Any questions? Guess not. Anyone care? Yeah. Okay. Okay, so, okay, we're making good time. I don't want to run out of time. So the next thing we want to do is break into UBoot. Now we have serial connection on the device. We can watch the device boot up, and we'll do that in a minute. We'll go through, watch the device boot up. Because in the boot up process, you see a lot of interesting data. You can identify, in this case, you can identify often the chipsets that are actually used. You can identify where it's loading stuff into memory, where it's executing data in memory. It'll actually lay out the partitions a lot of times as the system boots up, so you can define the various partitions that are defined on the flash chip. So it's a lot of useful information that you can use later on for attacking the device. So one of the things with boot, when a device boots, there's this functionality called boot delay. Get it right here. Boot delay, the second one down there. So most devices have boot delay set to 0 or turned off, okay? And when they do that, you can't hit a key. If it's set to anything other than 0, it'll come to that spot during the boot, and it'll start counting down. And during that countdown, you can just hit any key, and you can break out into UBoot console. So the protection routine for most UBoots is to set this to 0 or not set it at all. If it's set at 0, the interesting thing is, and this may work in rare cases, you can like Control-C or Control-D as the system's booting up as fast as you can and cause an error condition. It'll cause it to drop into UBoot if it's set to a boot delay of 0. But if the system is fast and boots fast, you're not going to pull it off because the response and the reading of the keyboard on the UART is so delayed, it probably wouldn't work in most cases. It won't work on this one here. You probably could. Yeah, I mean, there's a number of ways of doing that. Yeah, so, yeah.
What is default?
What's that?
What is default input delay? Default is 0 or default is 1?
Well, ever who designed the equipment. This is defined on UBoot. See, that's a UBoot environment variable that's set in here. A boot delay of 0. It all comes down to the manufacturer. I've seen them set at 3, I've seen them set at 5, I've seen them set at 0. I've seen them not in there at all, okay? Boot delay, UBoot also is not a standard package. Every install on every device I've looked at, almost inevitably UBoot, they compile it with the functionality and the command set that they want to use. So I've seen them compiled with everything, and I've seen them compiled with very little. So every manufacturer device will define what they want their UBoot to look like, and they'll define what they want their UBoot delay to be set at. Okay, let's see what we got here. Okay, so one of the attacks, and I think a number of you see me do this on a different device on a U, but this one is very similar, and the way to break out of a boot sequence when boot delay is set to 0 is UBoot, if it errors out loading the kernel, will actually fail into its console. The exceptions to that. I think the latest version of UBoot actually will just cause the device to keep booting. Okay? I have yet to find a vendor actually using the latest version of UBoot, and I probably tear apart 40, 50 devices a year. No one's doing it. The other thing is if they're using secure boot or a secure version of UBoot, there's kind of an add-on functionality that can be compiled into it that gives it a level of security. Those cases will not allow you to drop into the actual console. But the way we get in there is, if we look at this WinBond chip up here, this happens to be the memory chip. In this particular case, that contains the kernel. What I'm pointing at is pin 2, which is data out. So it's data being read out of the flash chip at that point there. So the way the attack works is when the device boots up, UBoot loads. And then once UBoots load, it makes a call to the kernel, which happens to be this particular flash chip. And at that point, if you short that pin out, pin 0 to ground, no data can get out. At that point, it can't load kernel to force the device to fail into a UBoot console. That doesn't mean you can go into one of these devices and just start shorting shit out. Okay? Know what you're shorting out. That philosophy will most often end up with a brick device or a smoke device. Now, I've used this attack before and have it fail. I was doing an assessment here probably about 6 months ago, and we had a device, and I was trying to force it into UBoot. And I went through this process, exact same chip, and it was all coming off the same chip. So it wasn't like I had a separate UBoot chip and then a kernel chip. It was all one chip. So timing is everything. So you could easily do it 100 times before you get it to work. I made it about 60 times before I totally wiped the UBoot out. It just went away. At that point, it wouldn't do nothing. It would just come up to a point and failure loading boot image and didn't go any further. We solved the problem by pulling the chip and then reading the memory. Because apparently I didn't destroy the chip. Well, I may have totally mussed the chip up pretty bad. We pulled the chip, dropped it into a really high-end reader, and it said, I have no idea what this chip is. I told it what the chip is, and it said its ID doesn't validate correctly. I said, well, just ignore it anyways, and it still dumped all the memory out. So that's the difference between a cheap $100 chip reader and a $4,000 chip reader. So I think the next phase is we're actually going to get into the demo stuff. Okay, we're running out of time here. And we got this powered up. Unplug here. Get out of there. So what we're going to do now is we're going to go ahead and hook a FTDI device. This is a Shikra UART FTDI device. It happens to be one I like to use. And let's see this thing boot up. The interesting thing when hooking UART up, you have transmit and receive. So when you hook into a device, it's important you hook transmit to receive, receive to transmit, so they're crossed over. If you hook it up and you turn it on and nothing happens, swap them. It's usually the fix. Okay, got to pick the serial port 115200, which is what we determine when we use the logic analyzer. And we're going to have connect the device. Okay, we need to refresh this. Okay, there we go. Let's go ahead and put power to it and see what happens. So as this boots up, we're going to see a lot of interesting things come through here. Sorry about that. That was the first one with a bunch of zeros there, happened to be the UBoot chip and its structure. I think it went through pretty quick. There's an interesting field right there where it says press, use F1 key to hit enter. We're going to look at that. You'll often see this show up on IoT type devices. And if we have time, we're going to jump over and look at that. Because it actually puts it in a single user mode, which basically gives you root level access to the device, which is cool. But remember, it's running at init 1. So there's no functionality, there's no network, there's none of that type of stuff. So it's still going at it. So the attack we're going to do today, as soon as this thing's booted up, we'll go back to it, is we're going to do the pin glitch. We're going to get it in the console, take a look at that type of stuff there. If you see me do the attack on the Hue device actually had the root password in the environment variables on UBoot. Really unusual, but it was just funny from a stupid standpoint. In this particular case, that's not it. So how do we get access? You can't crack these passwords. We've tried that. We've fed them into pretty good crackers. So, I've gone in and I've pulled the actual hashes off of it. We're able to crack them. So what we're going to do from this is I started thinking, well, heck, can I actually do a TFTP call from this device from UBoot and actually call a kernel from another image that will load up and give me root access with the goal to be able to get access to the actual memory chips. So what I'm going to demo about half works, let's get it right at half works, because we have 2 chips and I still haven't had time to go back around and define some settings and recompile my kernel image, because you have to define the actual chip and the device tree correctly, and there's a lot of methods for pulling that data, which we pulled the data, we just haven't gone in, and we have to rewrite some HCE files, I can't remember, I think they're HCE files, to actually build that chip into the image for compiling, which is something we're going to work on, but we haven't done that yet. But we're still going to show the process. So see, we get a root log on, we don't know what the password is. We want to get leveled access. So let's go ahead, clear this data, unplug the power. Switch over to another microscope, USB microscope. So here happens to be that flash chip. And here we have a grounding probe. It's all hooked up to ground. And what we would do is when the thing boots up, we would short this pin out right there. So that's the goal. But we have to know where we're at, so we can look out of the corner of our eye and see whether data's starting to flow here or not. Let's see if we can get it right the first time. I usually don't when people are watching.
Did you make your sacrifices?
Boom, got it. So here we've dropped out to the UBoot console. As you can see, error, init, error, so empty detection. So it basically failed trying to gain access to the kernel chip. Here we have a lot of environment variables. So we can look at the environment variables in this particular case that set up a number of different things. Here is the boot command. When boot delay is activated, that's the only time boot command will actually work. So if there's no boot delay on the system, the boot command does not work. You have the baud rate here. We also have environment variables. Let me see. Some of the most interesting environment variables, and I don't see them anywhere. Where are they at? Okay, scroll past that. Product test, MD parts. Okay, boot args right here. Boot args. These are the arguments that are going to be passed to the kernel or during the boot process. In this particular case, it's just defining the root file system here. What you can do, if you gain access to UBoot, and this will work on a number of devices, at the end of the boot args, at the very end, if you put a number 1, some UBoots will cause that to be read as the init level and will boot up in single user mode. Other options are S. You can put an S in there, lowercase or uppercase, and E, or the word emergency, or the word single. It varies from different UBoots. This particular case, none of those worked. We did get a certain thing to work, and I don't know if I'm going to have time to show it, but hopefully I will. And it put it into a weird state where you really didn't have access to anything other than the password hashes, I think. Okay, so now we're in here. We can set boot delay. I want to go ahead and do that in this case here. So we're going to set boot delay to 5. Wrong. Okay, get the right command in there. Set env, set environment variable, boot delay 5. We do print env. We can see our boot delay is now set to 5. At that point, we want to save env, which is save the environment variables. So here we can see we're actually wrote back to the chip. At that point, we should be able to hit reset, cause this device to reboot. And then we could hit enter and break out of it. And that way, if you're actually, keep you from having to keep glitching the pin, just set boot delay. At that point though, you're gonna have to set the boot arguments. You'd have to, where I said the boot command, you want the thing to boot up. It will work now because it has IPQ in there, boot IPQ, which is the correct boot image. So one of the other things, let me see where my stuff is. Oh, right here it is. Okay, since I don't like, what we want to do is we want to ping, okay, hold up, print env. So if we come over here to print env, we can see right here server IP. This is actually a TFTP server setting. And this device is IP address is actually set here in this environment, so it'll actually work. So I want to actually ping, because it won't work if I can't get to my server. Is alive, okay. So what we're going to do is we're going to put this TFTP in there. It's going to call from my TFTP server, which is right here. You can see the boot IDB right there. IF config. So let's see if this works. And it's going to load all this into the memory at 88000000, and then it's going to the AND command and boot M at that memory location if it works. And I hate when this thing does that. It's really weird. So now it's loading. So it's calling everything from the TFTP server. And this is OpenWRT. It happened to be, we're using an IPQ40 processor on here, which if you watch the boot image come up, you can see that it defined an IPQ40 something, I can't remember the number after that. That happens to be a kernel image available out there for OpenWRT. But like I said, it's not fully functional. I worked with a whole bunch of what had already been built, seeing how they were structured. I only found one other that actually called more than one flash chip. So the sad thing is everything I found out there was really a poor example for trying to figure it out. And for defining secondary chipsets or secondary flash chip on the device, there's even less documentation out there on doing that. But I did contact a few people I know, got access to some documentation on possibly building that, even though none of them had ever done it. They happened to know where the documentation were, and they understood it conceptually. So I have that at home right now, with the next goal is to recompile this image so that we can get access to that second NAND flash chip after boot up. Right now we'll have access to the boot chip, the UBoot chip, and we'll show that here in a second. If it comes up, boom, there we are. So now for the most part, we're root on the device, but we don't have access to all the data that we want. But typically you would gain access through proc/mtd. And this will actually show all of these structures that we have access. This particular flash chip really runs up to number 7, even though we're defining a kernel and a root file system. The kernel load up happened to be this one. See, if we look at the root file system, see the size of it, 000, 0000. That's because that secondary chip that we had over here, that chip right there, which happens to be, I don't know if we can get this show up. There we go. You can see the number on it right there, that 5F1G0. There's actually no build structures for that chip out there, so I have to define them into the device tree, which will be the next step for doing this. So any questions on that? So the general aspect of the attack is we want to be able to get some kind of root level control on the actual device to possibly get access to firmware, data, manipulate the device, maybe once we get access to the file structure that would be part of this device, we'd be able to get system calls that this device uses to call back home to the clouds, be able to gather that data, be able to do replay attacks. So it'd be in-memory access control of a device within its ecosystem. I know guys have done similar stuff to this on engagements where they're able to get root level access through these methods to get the passwords and stuff, to gain access to the high-end IoT technology, where they're able to use that to pivot back into the cloud and take over every device on the face of the earth that this manufacturer had produced, or at least gain level of access to do such a thing. So there's a lot of valuable test capabilities in here. So if this was not just a mesh Wi-Fi, but really tied into the cloud as some kind of IoT technology, one of the benefits I'd have at this point here is I could also possibly modify the data that's on the chip, putting my own keys on there. As an example, SSL keys, so I can structure man-in-the-middle attacks, so that I can see all the communication between this device and the cloud and decode it. Because typically it's going to be encrypted, and you're not going to be able to capture it, at least unencrypt it, without putting certificates on it and forcing it through something like Burp or some other proxy service to gain certain levels of access. So this is typically some of the attack vectors we want to go after. The bad thing often when you're dealing with these devices and we have that memory on the chip and you get to this level of access, most of those file systems, especially if they're squash file systems, are not writable on the flash chip. So in those cases there, what you would have to do is extract the squash file system, explode it out, modify it, squash it back up, and then DD it back onto the chip, and then boot up the system, which we've done a number of times to gain various levels of attack on a particular device. So those are some examples on how we would leverage these type of things to gain some level of root access. The next one I want to show is the one dealing with the F switch that we pointed out. Any questions?
So once you compromise this, does this provide an advantage to do lateral traversal within the mesh as well?
Yeah, it would. At this point, you know, once you get to this level here, you get access to the firmware. The big thing is get access to the firmware, because once you have that, then you can pull it off, you can modify it, you can put it back on, you have all this level of control. Once it's back on there, you can actually set up things like SSH and set up your own keys on the device and set up SSL, TLS keys. You have all these capabilities once you have this level of access. Once that's done, you've modified the system. At that point, you can come in externally, you can set your own accounts, passwords, which is things we've actually done on devices to get that level of access. At that point, you are part of the system and you have full control of what's going on in the back end. Most of these type of technologies, when you get into the hardware, especially with IoT, it's machine-to-machine communication. You as a user often don't always interact with your technology directly. You interact through the cloud. So it's all machine-to-machine, and you're interacting with APIs in the cloud. They're interacting with the back-end machine, and then it's machine-to-machine communication on the device, which then uses to control various sensors, detectors, lights, things like that on your actual network. So actually owning that machine gives you immense capability of looking at what are the communications going back and forth from machine to machine, which often have really bad security problems. Because no one's thinking that, hey, you know, they're going to screw with user interactions. They think machine to machine communications secure because it's in the background. It's back there. No one can figure it out. But once you're in the system, once you control the system and you can manipulate the machine to machine communication, you capture, you can decode it. At that point, it's game on, exactly. Game on. At that point, you can figure out what's going on and you can build an entire attack scenario. Because often what that machine's connecting to in the background isn't hidden on the internet. That only allows that device. Once you have that data and concepts out, now I can engage those API structures and systems directly as if I was the machine. Okay, let's go ahead and reboot this. Any questions?
It is incredible. I'm always fascinated with you. But what from attacker point of view, what kind of use for attacker of this? You need to have access to device.
No, it's a lot of people think that. Here, let me capture this real quick. See if I can get this.
My question is about practical use of this from attackers.
Yeah, just a second. I want to make sure I capture this so I don't have to reboot it. There we are. Now we're in. Okay. The practical nature is everyone assumes that, and your question is a perfect question, and I get it all the time. I'm going to hack you by physically attacking your system, and the answer is no. What I'm going to do is I'm going to set my own system up. I'm going to gain access. I'm going to map out all those communications, all those structures, and I'm going to test them for various vulnerabilities. Once I'm done testing those for vulnerabilities, at that point, I've gained enough information about how that whole system works, how the back-end system works, how the APIs work, and typically find many vulnerabilities. Now I can attack anyone using that product on the face of the earth. But the goal is not to attack all these people. The goal is to work with the vendor, get them to fix these problems, which we do quite a bit. I have an advisory coming out later this month that I think is kind of cool. It's dealing with a home security lock, one of the Bluetooth locks, where we actually found issues in the APIs where Let's say you want to grant access to your house for an hour, so you send somebody a key and they have that key. That person can now make an API call to the cloud and pull down the keys for everybody you've given permission to. And if you lock his account, he can still make all the API calls uninhibited. The only way to stop him is to delete him altogether. The problem is the way the whole system worked is keys are all based on a UUID that's generated as part of the application install on your mobile device. And that is your functioning key forever. Once it's compromised, you can take the app off your phone and reinstall it. It gives you the same damn key because it's based off something on your phone. So once it's compromised, game over. You're not getting over it. And that was just one of the things. But another example was a lighting system I was looking at. The lighting system turned out, when we started looking at all this communication, we found out data was being passed to a system in the cloud about the device. It was just posting data up. It was totally unauthenticated. It was a post process. So what I did was I took that post process, changed it to a GET process, and queried the same functionality with the UUID of the device, and it came back with information about that device, unauthenticated. Then I truncated the API call and removed the UUID request. Next thing you do, it came back with 25 responses of data from the last 25 people that engaged that system, including device numbers, device UUIDs, email addresses. So by analyzing these structures, this data, you get a bigger understanding of issues and vulnerabilities that impact everybody. Okay, so now we're here and we're root on this device. Now we're going to go ahead and we're going to plug this USB in here. See if we have time. So this is where I was. And see, it comes up with a USB. It tells me all this stuff about USB. There's one little problem. So if we ls, when I say L, SD splat, there's no devices. Oh, let me get it right. ls /dev. There's no SD devices. So even though it supposedly said it understands this, I still can't address it or talk to it because there's no freaking device out there. So I was at this pace here and I'm like, okay, I want to be able to pull the firmware off this device. I have a USB, I have an Ethernet. I could not get none of the Ethernet functionality to work, period. You know, because none of it's built, none of it's structured. If I raise the init level, it's going to challenge me for a password. It's a squash file system. I can't overwrite the password from here, and I can't crack the password. So how do we do this? So I started digging, and I found out, after learning how to understand some of this stuff pretty good, let me see. The first step is we actually have to define a device. We have to define it by a primary and a secondary identifier. Primary 8 means it's an SD device. Secondary, the 1, actually defines the number 1 device in the string. We set the right 666 to the device, pretty much. Okay, so once we've done that, we've actually created the device, and then we can actually do a quick check. I'm just speeding things up by not typing all this crap. So at that point we can see, hey, there's a device there. The device name is dev, SDA1. So now we've actually created a device. To make things better, we need to go ahead and format the device. So we're going to format the USB on here. That was quick. I don't trust that. Oh, no. Oh, it's creating. There it is. Okay, it's still working. It says creating journal. So it'll take a minute to do that. So, did it finish? No, it's doing superblocks now. So it's building all that structure based on the file system that I requested. And then now we've created this device. Our next step is we'll create, in embedded devices, there's only certain places you can put writable structures, and that's under temp. None of the other file systems are typically going to be writable. Temp is an in-memory structure, so that's where you would do all external mounts, and that way they're readable and writable. And then once we do that, then we can go ahead and actually copy a copy of the kernel image off this device. Okay, there it finished up.
Is there any devices I have a question.
What's that?
Is there any devices using any other OS but Linux?
Other OS?
Yeah.
Yeah, you're going to run into devices, various flavors of Linux. You're going to see Android's a big one. I run into a number of these devices, IoT devices, that are pure Android operating system. Those definitely add a little complexity to things. The saving grace is they don't use the current full file system encryption structure that phones use, which is a good thing, because if it did, it would like totally screw you over. Yet, trust me, yet, it's going to change. And let's come over here. And then we mount it up. It mounts up. It did a couple tests. It failed, and then it mounted it up correctly. And then what we want to do is, let's go ahead and cat/proc/mtd. Now here, since we booted up in full mode, we're actually going to see everything here. And as an example, we'll go ahead and the structure of, or the method is always DD. Reason why DD, well, I can't say it's always the reason, but DD is used on every device I've ever opened up, and this is how normal firmware updates come in. You will actually, if you look at this, if you look up here, you'll actually see that there is a UBI root file system data, there's a kernel 1, there's a kernel in the root file system, so everything's duplicated, as you can see. And the purpose of that is so that you can do firmware upgrades without bricking the device. So what will happen is, every time the system boots up, UBoot will load one of the structured systems, primary or secondary. Whatever one's not loaded up is taken offline, is always offline. The incoming firmware update will override that. Then UBoot environment variables are updated to tell it to switch over, and then when the device is done with the update, it reboots to the new kernel image, okay, the new file system, new structure image. If that fails, UBoot will crash, drop back over to the other one, and come back up. That way you don't brick your device. So to actually DD an image on and off a flash chip or a partition, it can't be mounted. It's unmounted, and then you partition it, yes?
Can you say they push a firmware update that breaks your access and you force it to roll back?
It'll usually automatically do it. If it's a normal firmware update process and it kills that and messes it, it tries to boot into it, it's corrupted, it'll normally crash out and fail into the other one.
I think if they like fix your vulnerabilities in your exploit, you force it to roll back to the old version that still has an exploit.
Sometimes you can with the environment variables. So if you go into environment variables and look for environment variables that defines which, it's either marked 0 or 1. So it's one of the two boot images it's going to use, kernel boot images. And that may vary too on how some of these systems call it, name it, all that type of stuff. But I've seen some that are very specific, image 1, image 0. But they're not always like that. Sometimes they are scripted because environment variables can be called anything you want for the most part. Okay, so now we've actually wrote that over. So let's go ahead and go over to temp. And we can see that there is, was that it? Yeah, I guess it was. No. Oh, okay, I didn't even see it. Okay, there you can see MTD-DIN, which is the root file system that we actually able to copy over. So that's one way you can actually get all the firmware off onto a USB. But in this case, we're literally forced to actually rebuild the entire device structure for the device to be able to be usable. And then we had to mount it up. Because typically you plug this in, it's going to mount automatically under media. Okay. It's going to mount automatically under media, but there is no media file structure. Okay. So there's nothing for it to mount up under. So we had to actually create the device. We had to format the drive, mount the device up under temp because that's the only read-writable structure on typical embedded devices. Isn't always the case. I've seen exceptions to that, but typically that is the case. In some rare cases, based on the operating system structure, there is a way to remount some of these partitions writable. I've only come across maybe 1 or 2 devices that actually worked on, but it came in handy because it was like, hey, will this work? And remount part of the key file system structure in a writable mode and was actually able to alter things on it. So it was kind of cool. But that's not always the case. Often you have to deal with the fact that it is not writable. Any questions before we finish up?